there, Wind Power students. Dr. John Schrage here, and we're going to be continuing today to talk about some of the basics of the atmosphere. And one of the things we're going to talk about today is the vertical structure of the atmosphere. Now, what we're talking about when we talk about the vertical structure of the atmosphere in general, we're talking about how things change with respect to height in the atmosphere. We're going to be focusing primarily in this particular lecture about how temperatures are changing with respect to height, but we could have talked about when we will be talking about things like wind and how wind changes with respect to height and the other properties of the atmosphere, how they change with respect to height in later lectures. And here the term with height means like as you go up in the Earth's atmosphere. Now, the actual temperature profile, what the temperatures are as you go up in the Earth's atmosphere, changes from place to place and from time to time. That's why the National Weather Service has to launch weather balloons with instruments on board that actually measure the temperature at different heights of the Earth's atmosphere. But if we wanted to kind of have a good sense of what a mean temperature profile in the Earth's atmosphere would be like, I like what I have right here on this slide here. Now, notice that this is pretty darn tall. It goes up to about 150 kilometers up there. There are no 150 kilometer tall applications in wind power or anything like that, but just to get a sense of what the structure here is, one of the things I'm noticing if I look at my red curve there that is the temperature profile, what I'm seeing is that there are heights where the temperature is higher and there are heights where the temperature is lower. That seems to be the structure that we're talking about. And, well, why would there be places that are warmer and why would there be places where it is colder? Apparently there is some process that is adding heat at these different places. We're going to use a bit of atmospheric science jargon here. We talk about processes that are sources. A source, just to swipe a dictionary definition here, a source is a person, place, or thing from which something comes or can be obtained. In atmospheric sciences, we're talking usually about a process. Something is going on here that is a source of heat. And apparently we have different heights in the Earth's atmosphere that is a source. Now, to understand this a little better, I want to actually steal a couple slides from the intro class that explains a little bit about sources, a little more clearly, and how this tells us something interesting about what's going on in the structure of the atmosphere. Here I have a pool with just tons of people in it. And let's say for some reason all the little kids are at one end of the pool, okay? I don't know, for whatever reason, the lifeguard's got them all over there on that one end. And all the big kids are on the other end of the pool. Alright. So again, don't think about it in terms of like how deep the pool is or whatever. The lifeguard chased all the big kids over here and all the little kids are over here. Alright. Now let's say that what you are worried about at the pool is pee. You're worried about pee in the pool. Alright. Where is there going to be more pee and where is there going to be lots of pee? Well, in this case, the little kids over there on the one end of the pool, they're a source of pee, right? I mean, it's horrifying to think about, but hey, I got little kids, I got to take to the pool all the time, trust me. They're a source of pee in the pool. Alright, so one end of the pool is where the source of pee is. Now, the big kids on the other end are, hopefully anyway, not a source of pee in the pool, right? So, if we actually could somehow see the pee in the pool, what we would see is we have established some kind of pee gradient, where there is more pee near the source and less pee near the other end of the pool. Now, it actually gets a bit more complicated than that, because obviously it would depend on how like the water in the pool is flowing. I mean, if there's a big strong circulation in the pool, it will be mixing the pee all through the pool. Or if there's some place where there's like a filter that's removing the urine from the pool, that would obviously affect. But from just a very basic understanding of the start, apparently the concentration of stuff, in this case pee, in the pool is going to be closer to where the source of it is. Okay? That's a good place to at least start our understanding of sources. In the same sort of way, here's a campfire. There's some people gathered around the campfire. Some people are farther and some people are closer. The people who are closer to the source of heat, namely the combustion of wood in the campfire, are warmer, and the people who are farther from the campfire are going to be cooler. Now, again, it's more complicated than that. If there was, for example, a wind transporting the heat away from the campfire towards the people farther away, but as a place to start understanding this, we would say, hey, closer to the source means there's more of that stuff, in this case heat. Farther from the source means there's less of this stuff, in this case heat. So, if we're thinking about it in those sort of contexts there, then apparently there are three places in the atmosphere where there are sources, three heights in the atmosphere where there are sources of heat in the atmosphere. Now the top one, up there at 1, that I labeled with a 1 there, that's way the heck up there. That's like 150 kilometers up or more. And, you know, there's not a lot of air at those levels up there. The source of heat there is actually the absorption of exotic forms of radiation from the sun and cosmic rays and things like that, that are just easily absorbed by the atmosphere, that don't penetrate down to where living things are and so on. And those high energy rays, when they are absorbed up there in the first few molecules of the Earth's atmosphere, just drive the temperature really high. Okay, absorbing radiation warms the molecules up that do the absorbing. Okay. Well, that actually illuminates us as to what's going on there at location 2. Location 2 is about ozone. Ozone is a gas in the Earth's atmosphere that is very good at absorbing a particular type of radiation that the sun actually gives off a fair amount of, called ultraviolet radiation. We're not, again, this is not the purpose of this class right now to talk about different kinds of radiation, but you've probably heard of UV or ultraviolet radiation. It's the kind of radiation from the sun that gives you sunburn. It causes skin cancer, it causes crop damage. Long-term exposure to it is, you can't live. Life on Earth wouldn't be possible if it weren't for the ozone layer, which is so good at absorbing all of that ultraviolet radiation. But again, absorbing radiation makes the temperature go up. It is a source of heat at the heights of about, 40 to 50 kilometers above the ground, as I have labeled with number 2. Number 3, the high temperatures right down there near the surface. Most of this radiation from the sun, in the form of sunlight, makes it through the Earth's atmosphere and hits the ground. But none of the radiation from the atmosphere, from the sun, makes it through the ground and out the other side of the Earth, right? The surface of the Earth is really, really good at absorbing sunlight. So the surface of the surface of the Earth warms up by exposure to that sunlight, and then by conduction, that heat transfers from the surface of the Earth into the atmosphere. And just the atmosphere is cooler, the planet's warmer. You touch them together, heat transfers from the hotter object to the colder object by conduction. So we have 3 heights in the atmosphere where apparently there is a source of heat. Okay, that kind of explains why those places are warmer. And in fact, if you notice, then what that means is we get this zigzag shape to the temperature profile of the Earth, meaning that there are layers of the atmosphere where the temperature is increasing with respect to height, and there are layers of the atmosphere where temperature is decreasing with respect to height. Let me be clear about that term there. When we talk about a layer, we mean something that has thickness. It has a bottom and a top, and there's stuff in between. That's in contrast to a level. A level is just sort of a height in the atmosphere, okay? So, alright, we have some layers where temperature increases with respect to height, and we have some layers where temperature is decreasing with respect to height. We're going to use a little bit more jargon here. We're going to talk about that in terms of the environmental lapse rate, or the ELR. The environmental lapse rate is something that we measure. That's part of the reason why we launch weather balloons with instruments that can measure the temperature at different heights. And it is defined as the rate at which temperature is changing with respect to height. It's just a change in temperature over change in height. You measure the temperature at 2 different heights, you take their difference. You measure the height at those 2 different heights, you take the difference. It's the how many degrees the temperature has changed over, say, a kilometer. It has then units of degrees Celsius per kilometer, or Kelvin per kilometer, or something like that. And it is defined to be positive when temperature is decreasing with respect to height. Temperatures decrease with respect... I know I would have done it the other way around. I would have said positive means it's getting warmer with height, but you'll see why in just a minute, as to why they defined it to be positive means it is decreasing with respect to height. So here's my temperature profile in the Earth's atmosphere. Again, it will vary a little bit from day to day and things like that. That's why we launch weather balloons, but this is a pretty good approximation as to what it usually looks like. Now, if we were to take a look at this here, we would see that the lowest part of the atmosphere, where like all the wind power is done, the lowest maybe 10 weather happens, it's part of the atmosphere, everything, wind power happens, etc. Notice that temperature is decreasing with respect to height. So by our definition of how we work with the signs of the environmental lapse rate, the environmental lapse rate is positive here. In fact, that's why we defined that to be positive. Early meteorologists only could get into the troposphere. We didn't know that there were other layers higher up there where the environmental lapse rate would be the opposite sign. Alright, so why is it called the troposphere? Tropo is a Greek prefix that means something like turning. A heliotrope is a type of flower that turns during the course of the day to face the sun. Agiotropism is a phenomenon you learned all about in like 4th grade science class, where seeds turn over so that the roots grow down and the green parts grow up. Okay, it turns away from the earth to agiotropism. Trope, it means turning, and the troposphere is full of all kinds of features that are about twisting and turning motions, cyclones and anticyclones and tornadoes and hurricanes and dust devils and so on. So it's the troposphere. Now, the top of the troposphere is called the tropopause. The troposphere is a layer. The tropopause is the top of the troposphere. It's just a level. Alright, sitting on top of the troposphere is a layer of the atmosphere called the stratosphere. It extends from about 10, 11, 12 kilometers up to about 50 kilometers up. And in this layer, temperatures are increasing with respect to height because we're getting closer and closer to where ultraviolet radiation is being absorbed by ozone. The environmental lapse rate is negative because because the temperatures are increasing with respect to height. Again, early meteorologists couldn't get to the stratosphere. It was discovered only like 100 years ago or something like that by a balloonist named Léon Tesseron de Borch, a great name. The stratosphere, why do we call it the stratosphere? Strato is a Greek prefix that means something like smooth or layered or laminar or something like that. Very smooth. And basically nothing weather happens in the stratosphere. Again, we'll learn later in the semester why this is not a good place to have weather, but it's very little turbulence. It's why jet aircraft tend to fly in the stratosphere, because you're going to have a smoother, more efficient flight with very little disruptions of your path due to weather features, very little disruption of your path due to things like turbulence and so on. The top of the troposphere was called the tropopause. The top of the stratosphere is called the stratopause. It is a level that is the top of the layer that is the stratosphere. See the pattern here? Alright, sitting on top of the stratosphere is a boring layer of the atmosphere called the mesosphere. Meso just meaning middle, so it's sort of like the middle atmosphere. In fact, that's a terminology that like rocketeers use and things like that. They describe that as the middle atmosphere. It goes from about 50 to about 90 kilometers above the ground, and frankly, not very much happens in the mesosphere. Temperature is decreasing with respect to height, so once again, it is a place where the environmental lapse rate is positive, but not much of anything happens there. There's not a lot of air molecules by the time you're 80, 90 kilometers above the ground. So the top of the troposphere was the tropopause, the top of the stratosphere was the stratopause, the top of the mesosphere is the mesopause. And then finally you get to the really crazy layer of the atmosphere, the thermosphere, which is above the mesopause. It starts at about 90 kilometers and just goes and goes and goes. I mean, the diagram here goes as far as 150 kilometers, but I mean, some textbooks have a diagram that goes to 500 kilometers. But, you know, wait, doesn't the International Space Station orbit at like 300 kilometers? Yeah, we're talking some pretty thin layers of the atmosphere here. I mean, the International Space Station orbits in the thermosphere. I mean, there are air molecules there, just not that many compared to the thicker, gooier parts of the atmosphere down lower. It is a temperature inversion. That is our word for a layer of the atmosphere where temperature is increasing with respect to height. The temperatures just get very hot because of the absorption of all these crazy types of radiation, cosmic rays and stuff like that. Not that there's so much of that stuff, but there just aren't that many molecules. It's a small amount of radiation, but there aren't that many molecules to heat up. So temperatures just get hotter and hotter and hotter the higher up you go in the thermosphere. This structure is fundamental to meteorology. There's all kinds of important things that an atmospheric science major or an atmospheric science graduate student would need to know about all these different features and so on. But, you know, honestly, even those low features, like the tropopause, for example, well, that's like 11 kilometers above the ground. Well, that's way higher than anything used in power production. All of our power production is down in the troposphere. I mean, for example, okay, I'm sure this was obsolete as soon as I found it, but I just Googled what's the tallest wind tower, and you can follow this link if you want to. The world's tallest freestanding wind turbine is 720 feet tall at the time of this in 2014 that I found this page here. You know, what about those airborne wind turbines? I mean, don't you picture those things being really high? Oh, well, this current one here is going to be 1,000 feet high. Okay, 1,000 feet versus 11 kilometers, right? Obviously, all wind power production is down here in the troposphere, which makes sense. Even if there were strong winds way up high, like in the stratosphere or something like that, remember, the kinetic energy of the wind, which is where you're getting your power, depends not just on the wind speed, but on the density of the air, and there's just not that much air up there. So we aren't going to be generating wind power up in the stratosphere. It doesn't make good sense to do those kind of things. We're going to be generating wind power in the troposphere, and in fact, probably down low in the troposphere, down closer to the ground. Well, as it happens, there's parts of the atmosphere down closer to the ground, parts that I love. I am totally interested in this part of the atmosphere in my research and stuff like that. The lowest part of the troposphere, the lowest kilometer or two of near the surface of the Earth, is a part of the atmosphere called the boundary layer. Now, your textbook gets all kinds of sloppy here. Sometimes it calls it the planetary boundary layer, or PBL. Sometimes it calls it the atmospheric boundary layer, or ABL. But they're all the same thing, okay? It's just different groups of scientists tend to prefer different terms and so on. But the boundary layer is the part of the atmosphere that's actually in contact with the ground and takes properties from the ground and interacts with the ground. That means that it has a diurnal cycle. Diurnal, as in over the course of a day. It is hotter in the boundary layer during the day. It is colder in the boundary layer at night. That might not seem like rocket science until you realize that's not the case in other parts of the atmosphere. Say higher than the boundary layer, maybe 6 kilometers up, let's just say. It's not warmer during the day than it is at night. It's not windier during the day than it is at night, the way it is in the boundary layer. There's no diurnal cycle to the atmosphere outside of the boundary layer, with a few minor exceptions of a few small processes and so on. So the boundary layer, that lowest kilometer or two, this is the one that's going to have a daily cycle. As it interacts with the temperatures and the surface of the ground, it's going to have daily cycles to things like temperature, humidity, wind, air quality, and so on. It is somewhat complicated as to how deep the boundary layer is. In fact, there's a number of processes that determine how tall or how low the boundary layer is, but it extends from about 1 kilometer to about from the surface to about 1 kilometer to maybe the surface to about 4 kilometers. 4 kilometers would be a pretty thick boundary layer. But the boundary layer is this changing layer of the surface, of the atmosphere near the surface, where it can be shallower, especially at night, and it can be deeper, especially in the afternoon, but it ascends from the surface up to the to that level. Now, the rest of the troposphere above the top of the boundary layer is a layer of the atmosphere called the free atmosphere. So the free atmosphere extends from the top of the boundary layer up to the tropopause. It's the rest of the troposphere. And the free atmosphere doesn't really experience any of the interactions with the surface of the Earth. That doesn't mean the surface of the Earth is unimportant, it just doesn't directly experience it itself. That air doesn't touch the ground. It is not experiencing the fact that the ground is hotter during the day and colder at night. It doesn't experience the fact that there are changes in the amount of friction and so on. We'll be learning about all these things. Even at its shallowest, the boundary layer is 1 kilometer thick. None of these features that we talked about with wind power extended outside of 1 kilometer. So any planned wind turbine or anything like that, we're going to be interested in the boundary layer. In fact, the boundary layer itself has a structure. In fact, the boundary layer has a fascinating structure as it grows and changes over the course of a diurnal cycle over the course of 24 hours. Now, at the present time, your book is just taking a very simple idea here. We're going to get a lot more complicated of our understanding of the boundary layer as time goes by. But the boundary layer can be, in a very simple sort of way, can be divided up into the surface layer and the Ekman layer. So if you take the boundary layer itself and divide it up into 2 little pieces, the surface layer is where the log wind profile happens. What do we mean by the log wind profile? Well, we're going to learn all about that in a later module, of course, but the log wind profile is about the business of how, like, as you go up in the atmosphere, the winds are increasing. And in fact, as you go up in the atmosphere, they are increasing in a particular way that is shaped like a log curve, like a logarithm or whatever. Actually, that's kind of an oversimplification. There's even more interesting things that can happen to the wind, but that all happens in this surface layer. The surface layer is maybe from the surface to 50 meters, maybe surface to 100 meters. It certainly is in the layer where we put wind turbines. It certainly is in the layer in which we have, antennas and other things that have wind load that we have to be worried about, or even structures and so on. So this is certainly often important for wind power. In practice, though, actually wind power, tall turbines can get out of the surface layer and up into the Ekman layer. Ekman layer is another part of the boundary layer. Again, it still is going to have a diurnal cycle of temperature and wind and turbulence and air quality and humidity and so on, but it is not actually touching the surface. It's from wherever the top of the surface layer is to wherever the top of the boundary layer is. The term Ekman layer is kind of a wind power term. Meteorologists don't tend to use that word, although I could see why they have it. Meteorologists would actually divide this up because the Ekman layer works very differently during the day than during the night. And again, we'll see more about this over the course of the semester, but you're going to see that during the day, a much better word than Ekman layer is the mixed layer, because of all the mixing that is going on in there. Whereas during the night, a much better term for what's going on in the Ekman layer is the residual layer. But we'll get to all that. We'll pick that all apart as we hit it over the course of the semester. But wind turbines do reach up into the Ekman layer. And so we will need to be able to understand some of its properties and how its winds are affected over the course of the day and so on, and figure out if this is a good place to be generating power and so on. But all of this is a grotesque simplification of what's going on in the boundary layer. I mean, the boundary layer is an enormously complicated part of the Earth's atmosphere that evolves rapidly over the course of the day as sun angles change and the sun comes up, as water evaporates off of the surface, as turbulence starts generating, warm and cold thermal plumes develop, and so on, all of which will have enormous consequences for what's going on at the surface with regard to our ability to generate power and so on. Oh man, in case you haven't figured it out, boundary layer stuff, I am totally all about that. And I'm going to be telling you more about the research I do about it and so on over the course of the semester, which is really interesting because it actually, will be very tied to how we generate wind power and so on. But in the present time though, let's say that we're done with this lecture here, and we're going to ask a couple questions about what you just learned. Now this first question here might be a little bit tricky if you just, depending on the notes you took and so on. It says, put these features of the atmosphere in order from lowest to highest. Tropopause, mesosphere, stratopause, troposphere. Alright, and then I have 4 different lists of them there in slightly different orders. Put those things in order from lowest to highest. Make a choice from one of those 4 options and get a little feedback before you move on to question 2.